of stoichiometry. So ideally we would be doing this in during class time, but this is one of those things that I definitely want to make sure that we have enough time to talk about and for you guys to learn. So before we get started on stoichiometry, even though it sounds like it could be very confusing, I promise you, as long as you put in the time and we work through the problems, you're going to be just fine. It's one of really the three main takeaway things that I want you to say that you learned in chemistry. So the three things would be, do you know your elements? Which you do. Do you know how to balance and write chemical equations? Which we did. And then do you know how to apply those chemical equations with stoichiometry? So what is stoichiometry? We go to the next slide here. So stoichiometry, by definition, is just the study of quantitative relationships between the reactants used and products formed in a chemical reaction, and it's based on the law of conservation of mass. So in stoichiometry, we're really going to be looking at applying units 7 and 8, where we talked about chemical reactions and also the mole. Before we get into the flip chart and different types of stoichiometry problems, I want to just talk about a place where you probably have used and seen stoichiometry a lot in your everyday life, and that's any time that you've followed a recipe. So if I look at this recipe here, and this particular recipe, let's say, makes 2 dozen cookies, but I need to make 4 dozen cookies. What would we do with all of our ingredients? We would simply just double them, right? If instead of making 2 dozen, I want to make 4 dozen, instead of a cup and a half of sugar, I would use 3 cups of sugar. Instead of 1 cup of salted butter, I would use 2 cups. I would use 2 cups of sour cream, 2 teaspoons, 2 eggs. So basically, all of these ingredients are what we call our reactants, and then anything that I make, so in this case, the cookies, those would be my products. So don't lose sight of that as we go throughout these problems. Obviously, we're going to be applying them to stoichiometry and chemical reactions, but just don't lose sight of basically stoichiometry is just recipes. Whatever I start with is going to dictate how much of something I can make. Now we're going to look at just the calculations in this video. We're then going to talk about percent yield and limiting reagents in another video. So there's one thing that I highly suggest you make, and that is what I call a flip chart. And if we were obviously together in class, we would be making this together. But basically, you just need like a narrow sheet of paper. It doesn't need to be anything fancy, but you need to be able to have 2 flaps. So this middle section should stay. And I'll talk through what the B's and the A's mean here in just a minute. But if you were to close the flap, you should just see moles of A. And then you would multiply by this ratio, and I'm going to explain that here in just a second, and then moles of B. So if your flip chart is closed, this is what it should look like. These 2 flaps, however, should be able to open up, and then you can actually see this when it's open. So let me go through and just explain what a couple different things would mean. First off, this middle section is what we call the mole ratio, and I will be defining that here for you in just a couple slides. B versus A is always what we are given in the problem, and B is always what we are trying to find. So these are going to be specific for different chemical compounds. So it could be like water and oxygen, hydrogen and oxygen. So we're going to have a whole bunch of different compounds we use. So we just define A and B just to make it easier. So then we also have down here when it's open, I can actually get from grams of A to grams of B by looking at this grams per mole. So this should look familiar to you. Anytime we have the grams per 1 mole, that's going to stand for our molar mass. And molar mass we can get from our periodic table. So basically this is just a hands-on way to figure out and see where to put the numbers based on the dimensional analysis. So it's kind of like when we did conversions before. So you're basically multiplying. If I look here, moles of A, I want moles of A to cancel, so we always put them in the bottom right. So if you guys remember, like let's say I had 5 grams of something, I put grams on the bottom and I put moles on the top. let's just say it's a molar mass of 1.01, let's say it's hydrogen, my grams would cancel to get me moles. So this is basically telling us how to set it up in order to get to B, or the unit that I want. So I can go from moles to moles, I can go from grams to grams, I can do liters to liters, or I could do a variety of different conversions in there. So these are going to be the four main type of stoichiometry problems that we are going to see. We're going to start with the simple mole to mole calculations. We'll eventually get to mass to mass, which that's actually going to be our most useful type of calculation, because we want to actually be able to physically determine how much of something I should make, so that this is where it really becomes practical in the lab setting. And then we can get a variety of different mixed units. So before we get into the specific calculations, I want to talk about a mole ratio. And before I do that, I just want to look at this recipe. So let's say I wanted to make 24 brownies, and I know that if I combine 1 cup of flour, 4 ounces of chocolate, 2 eggs, and 1 cup of sugar, I make 24 brownies. So all of these would be my reactants, and then my 24 brownies would be my products. So basically what a mole ratio is, and we're going to see that here on the next slide, is just the ratio of reactants to products or products to products. So let's say, for example, I have 1 cup of flour. So 1 cup of flour, I could say for every 1 cup of flour I need, let's say I wanted to know my mole ratio between eggs. Well, here's my flour, here's my egg. So for every 1 cup of flour, I need 2 eggs. We could also say, if I have 1 cup of flour, how much sugar do I need? So for every 1 cup of flour, if I look here, I need 1 cup of sugar. If I wanted my flour to chocolate, I would say 1 cup of flour to 4 ounces of chocolate. So I can set up all of these different ratios between my reactants. We can even do it with my products to see if I have this particular thing, so in this case it's the cup of flour, how much of the other thing do I need? So when we do that in terms of moles, it's really just the ratio of coefficients in a balanced chemical equation. So that's why it's so important to remember how to balance chemical equations, because we have to know our coefficients, or the big numbers out in front. So for example, and if I write this here, I don't have a coefficient in front of nitrogen, so it's a 1 to 3 to 2 ratio between my nitrogen, hydrogen, and ammonia. So if I wanted to know my mole ratio between nitrogen and ammonia, we would say it's a 1 to 2 ratio because there's nothing in front of nitrogen and there's a 2 in front of ammonia. Let's say I wanted the mole ratio between nitrogen and hydrogen, so N2 to H2. We would just say it's a 1 to 3 ratio, because for every 1 mole of nitrogen, you need 3 moles of hydrogen. This is because it is the law of conservation of matter. Matter is never created or destroyed. So if I want to use those mole ratios then, and I want to go back to that flip chart, if I want to know how many moles of ammonia are produced when 0.6 moles of nitrogen reacts with excess hydrogen, the excess hydrogen for right now is not going to matter. It's just telling us we have enough. When we get to limiting reagents, that's where it's going to definitely become a lot more important that we actually understand what that means. But for right now, if I want to know how many moles of ammonia, so basically I'm going to be going from moles of A to moles of B, because we're just doing a mole to mole calculation right now. So if I go back up to my flip chart, sorry, I'm going to kind of flip back and forth here. I'm just going to use my flip chart close. The reason I'm going to use my flip chart close is because I start with moles and I want to end with moles. We'll eventually get to some calculations where we're not there. So if I start with moles of A is what is given, and I'm trying to find moles of B, it's going to be a one-step conversion using my mole ratio, which is what I just explained to you. So if I go back to this problem, whatever number I give you to start is what I always start with on the top left. So I tell you that I have 0.60 moles of nitrogen. And if you want to label that nitrogen as A because that's what's given, that may be helpful for you to see what is A and what is B. If I'm trying to find my moles of ammonia, that means I'm trying to find my product. So when I set this up, I always put moles of A, or whatever A is, on the bottom right to cancel. so moles of N2, and I'm trying to find moles of NH3. So you can either use the chemical formulas or you can use A and B. That is completely up to you, however you see it best. So in order to go from moles of one thing to another, we always use the mole ratio. So that's going to be our middle, most important part for any of these calculations. So for every 1 mole of nitrogen, I'm going to use a different color here, I produce 2 moles of ammonia. So that's my mole ratio. So if I cancel out my moles of nitrogen and I just multiply across, so just like when we did our other mole calculations, I see that I produce 1.2 moles of NH3. And that's my answer. Now again, how practical is that in our lab setting? It is not, but we'll eventually get to that in a little bit. All right, so we're just going to do 2 more problems here, and then I will continue with another video for the next part. So here's another balanced chemical equation. So that's always the first step, is to make sure you have that. The carbon dioxide exhaled by astronauts can be removed by reacting carbon dioxide with lithium hydroxide according to the following reaction. So here's my chemical reaction. I want to know how many moles of lithium hydroxide are required to react with 20 moles of carbon dioxide. So I really only care about my reactants in this case. I give you the carbon dioxide, so that means that's A, and I want to know how many moles of lithium hydroxide, so that's B. So I give you A, and I give you that I have 20 moles of that. So I have 20 moles of the CO2, and it's going to be a 1-step conversion to get to my moles of lithium hydroxide. So this is where I use my mole ratio. For every 1 mole of carbon dioxide, I need 2 moles of lithium hydroxide. My moles of carbon dioxide cancel. I'm left with moles of lithium hydroxide. So if I just multiply those out, I get 40 moles of lithium hydroxide. So just like the recipe example, if I had 1 cup of flour and I needed 2 cups of sugar, whatever the case is, if I scale that up or down, I'm going to scale my ingredients up or down with that.